from Waseda University, Japan, Dr. Muhammad Azuwa Muhammad from Universiti Kebangsaan Malaysia, Dr. Farhana Aziz from Universiti Teknologi Malaysia, and Dr. Norharyati Salleh from Universiti Teknologi Malaysia, and all the participants in the meeting series today. Ladies and gentlemen, welcome to the World Class Professor Meeting Series with the theme Recent Development on Efficient and Effective Membrane Research for Enhancing Publication and Grant Winning. My name is Ikal Stari, and I will act as the Master of Ceremony in today's webinar. Before we come to the main session, let us start this by praying first. So, the event that we will hold on this day will run well without any obstacle at all. Pray based on individual belief. Begin. Done. Ladies and gentlemen, on this association, let me deliver the structure of the event today as follows. First, remarks for the segment of the World Class Professor Meeting Series, Dr. Muhammad Purwanto. Second, remarks from the head of the Department of Industrial and Process, Institut Teknologi Kalimantan, Himawan Wicaksono STMT. Third, photo session for the presentation of material and discussion session, the last closing. And now, the report event, it's my pleasure to invite the chairman of the World Class Professor Meeting Series, Dr. Muhammad Purwanto.
Oke, thank you Mbak Ika. Assalamualaikum warahmatullahi wabarakatuh. Good morning and greetings, respectable the Rector of Institut Teknologi Kalimantan, Professor Budi Santosa, PhD, Excellencies the Vice Rector of Academic Affairs of Institut Teknologi Kalimantan, Ibu Nurul Widastuti, PhD, Excellencies the Head of Department of Industrial and Process Technology, Bapak Himawan Wicaksono, STMT, honorable speakers, my supervisor, Associate Professor Dr. Juhana Jaafar from Universiti Teknologi Malaysia, and then Professor Dr. Sadaki Samitsu from Waseda University, Japan. Good morning, Prof. Thank you for your agreement of our invitation. And then Dr. Norharyati Salleh from Universiti Teknologi Malaysia, and Dr. Farhana Aziz from Universiti Teknologi Malaysia, and then my friends, my best friends, thank you, Mas Azuwa, Dr. Muhammad Azuwa Mohamed. Selamat pagi Mas Azuwa, jumpa lagi from Universiti Kebangsaan Malaysia, UKM Malaysia. And all of the invited guests, researchers, colleagues, and students from various institutions, and all the participants. Ladies and gentlemen, welcome to the World Class Professor Meeting Series. Beforehand, I would like to explain about the World Class Professor Meeting Series. The WCP is a future program issuing by the Indonesian Ministry of Education, Culture, Research, and Technology. This program, they encourage the Indonesian lecturers to enhance their competencies and contribution in the development of education, research, and innovation by inviting world-class professor in a period. I believe that today we will all receive useful knowledge and discussion on the webinar with the theme Reasons Development of on Efficient and Effective Membrane Research for Enhancing Application and Clearance Wining. In this webinar, we will learn about the recent research on membrane technology and its development to obtain funding source and successful publication in index journals. Once again, on behalf of the committee, we thanks all the speakers who have been willing to convey this important topic so that we can all increase our knowledge about membrane research and development. Well, I do not want to take too much of your time. I need to hand over it to Mbak Ika Lestari, our today MC. I would like to say once more on behalf of this seminar organizer, welcome. It is great to see so many of you here. Thank you and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for your report, Dr. Muhammad Purwanto. Next agenda is to formally kick off our event with the head of the Department of Industrial and Process, Institut Teknologi Kalimantan, Himawan Wicaksono STMD. Time and screen are yours.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh, and good morning, ladies and gentlemen. Thank you to each and every one of you here for being here today at this wonderful moment. Let me introduce myself. My name is Himawan Wicaksono. As chairman of the Department of Industrial and Process Technology, or we call GTIP. My department consists of 6 study programs, one of which is chemical engineering, study program that have received the world-class professor grant. Congratulations to Dr. Muhammad Purwanto and the team who were the pioneers in this implementing this event. Congratulations. The world-class professor or WCP program is a program that invites world-class professors from various well-known universities from within the country and abroad to be placed in the university in Indonesia for a certain period of time. This program is intended so that lecturers or researchers can interact with well-known and excellent professors so that they can improve their academic life, competency, quality, and contribution to the development of science and technology, and strengthening the national innovation system in an effort to optimally utilize the diversity and wealth of Indonesia's cultures, resources for the welfare of the Indonesian people. Let me start with a great welcome on the world-class professor meeting with the theme recent development on efficient and effective membrane research, publication, and grant winning. And before we begin, I would like to express my appreciation to the outstanding speakers, including Associate Professor Dr. Juhana Jaafar, Universiti Teknologi Malaysia, and second, Professor Dr. Sadaki Samitsu from Waseda University, and third, Dr. Farhana Aziz from Universiti Teknologi Malaysia, And fourth, Dr. Norharyati Wan Salleh from Universiti Teknologi Malaysia. And the fifth, Dr. Muhammad Azuwa Mohamed from Universiti Kebangsaan Malaysia. And not forget is Bapak Rektor Institut Teknologi Kalimantan, Prof. Budi Santosa, and Ibu Wakil Rektor Institut Teknologi Kalimantan, Ibu Nurul Widastuti, and the coordinator of the Chemical Engineering Study Program, Mr. Adrian Gunawan, and the lecturer of the Chemical Engineering Study Program, students, and webinars. And don't forget, thank you for the support from the Ministry of Education and Culture, Kemendikbud, as the initiator of this event. Okay, well, I do not want to take too much of your time. I need to hand over to the moderator. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you very much for your speech, Himawan Wicaksono, STMT. Before we continue, I would like to ask to all of the audience to do a photo session. It was hoped that participants would turn on the video and use the available virtual background. That is 2 slides. First slide. 1, 2, 3. Second slide. Thank you. Without ado, I will invite the moderator of today, who will lead the speech and discussion session. Please welcome Gusti Umindya Nur Tajala, STMT.
Hey, thank you, Ika, for your introduction. Hello, good morning. I'm Gusti Umindya Nur Tajala. We'll lead the speech session for today's webinar. Hope you are to all follow are in good condition. Nice to meet you all. Actually, I'm really excited today. Why? Because I meet all of the speakers, although we are in an online scheme. But still, it is such an honor for me to have all of you in this bright Sunday morning, because it is very hot in Indonesia today. As we know, today's theme is about recent developments on vision and effective membrane research for enhancing publication and grants winning. All of today's speakers are having excellent works on membrane technology or technology membrane in Indonesia. The dedication in membrane technology are proven with publishing in enormous high reputable journals. Also, I think the grants will come naturally not only from government, but also from private sectors. So let's hear together about their amazing job one by one. So first of all, I would like to introduce you to the first speaker, our beloved Associate Professor Dr. Juhana Jaafar. She is graduated with Ph.D. in Chemical Engineering from Universiti Teknologi Malaysia in 2004. And she was then granted with the National Science Fellowship under Ministry of Higher Education to pursue her MSc in Gas Engineering in Universitas Teknologi Malaysia. In 2011, she graduated with a PhD in gas engineering from the same university, specializing in membrane technology for direct methanol fuel cell application. She started her academic career at UTM in 2007, right after graduated her MSc. Currently, she is the Associate Professor in the School of Chemical and Energy Engineering, Universiti Teknologi Malaysia. She is also the Deputy Director of Advanced Membrane Technology Research, UNTEC, a higher institute center of excellence rewarded by the Ministry of Education Malaysia. Associate Professor Dr. Juhana is also active in writing for scientific publication in high impact factor in international and national journals. To date, she has published more than 285 papers in IC index journals with HI index of 32 and total citation of 3,452. Until now, she already led 30 research grants and being member of more than 100 research projects that worth more than 15 million ringgit Malaysia. Associate Professor Dr. Juhana has received several recognitions at a national and international level. Recently, she has been rewarded the Regional Conference Grant 2020 from UNCIT.net for organizing the Regional Congress of Membrane Technology 2020, a Regional Conference on Environmental Engineering 2020, in which she has the chairman of the conference. She has also received the UNCIT Alumni Mobility Grant 2020 from UNCIT.net. So without further ado, please welcome Dr. Juhana.
Okay, thank you, Ms. Moderator, Ms. Gusti, for the very nice introduction. Thank you very much. Yang saya hormati Rector of ITK, Prof. IR Budi Santosa, the Head of Department of Industrial and Process Technology, Pak Himawan Wicaksono, the Vice Rector in Academic Affairs of ITK, Ibu Nurul Widyastuti, the Coordinator of WCP ITK 2021, Pak Purwanto, and team, and also my fellow friends who also present today to present their work as well. And ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Okay, so let me share my slide. Okay. So inshallah, today I will share with you about this topic, freestanding TiO2, titanium dioxide hollow nanofiber photocatalyst for wastewater treatment. So I will be focusing on the BPA, bisphenol A, as the pollutant in the wastewater. Okay. So just a quick glance here. Okay, this is the statistic of publications from 2010 to 2021, which I obtained it from the Scopus database. So this is the findings when I use the keyword photocatalytic. Okay, so you can see the number of publications increase year by year. Same goes to this data, which I use the keyword photocatalytic and membrane, the integration of photocatalytic technology and membrane technology, meaning that we have two technologies in one, two processes in one technology. So as you can see here, the number of publications also increased year by year. So this finding shows that both fields are worth to be explored, right? So it's just that there is a significant difference here between them. As you can see, for photocatalytic alone here, the number of publication has reached more than 10,000 and it keeps increasing, right? So this shows that Scopus is still looking for more recent and innovative studies from us. Okay. Meanwhile, for photocatalytic membrane here, the number of publications is still below 400. And this shows that there are more rooms for us to contribute in this field. So, so there are more rooms for us to explore in these two fields, photocatalytic and photocatalytic membrane. But today I will be focusing on the photocatalytic alone, since that we have, the output or the findings of recent findings in this field. Okay, so as for introduction, sorry, this slide highlights some relevant numbers in water crisis scenario. So by fact, we have less than 3% fresh water that we can use for our daily life, right? So, and by 2025, world's population may face water shortage issue. And these are the numbers, as you can see, 2.4 billion, 2 millions. Then these numbers reflect the human that have gotten affected to polluted water. So in order to save the very less water that we have, so industrial wastewater treatment for water reclamation could be one of the solutions. Okay, so tertiary treatments such as advanced oxidation process like photocatalytic degradation process would be a promising method to remove toxic and organic compounds in the wastewater. So organic compounds that I'm talking about today will be BPA, bisphenol A. Okay, so bisphenol A. Okay, so this is one of the organic pollutant that we must treat from the wastewater so that we can reclaim the clean water for our daily use. So BPA is a chemical that is used as the plasticizer in the manufacturing process of products such as plastic water bottles, baby bottles, plastic utensils, and food containers. Okay, so BPA can enter our body through the food or drinks that we consume, and also through the industrial discharge into our water sources. Okay, so as BPA has the ability to mimic the hormones in our body and disrupts the body system, it is very important to develop an efficient water treatment technology for BPA removal, right? Okay, so I would like to share here, this is one of the recent data that has been published and conducted from a group from UPM, okay, Universiti Putra Malaysia, okay, in which they have found that in Langat River is very polluted river in Malaysia. So it's in Selangor State. Okay, so as you can see here, they tabulated the EDC. EDC is endocrine disruptors, and one of the EDC is BPA. So as you can see here, BPA content concentration in the Langat River is among the top 3 high concentration found in the Langat River. Okay, so here I would like to share with you the mechanism of photocatalytic degradation process. So as I mentioned just now, we have to find one solution to solve or to treat the BPA, the organic pollutant in the wastewater. So as I highlight just now, AOP or advanced oxidation process, one of it is photocatalytic degradation process. So I will highlight about this process, okay? So fundamental explanation is always the best explanation to discuss about the result or finding of a process, right? So it starts from the catalyst itself, which normally comes from semiconductor material like titanium dioxide. Like I said just now, I will focusing on the titanium dioxide. So the titanium dioxide will be the catalyst of this process. Okay, so just imagine this is the catalyst, the photocatalyst. So the catalyst that can work under photoirradiation must have this balance. This is the valence and conduction bands. Okay, so when enough energy from the light source, either a UV, solar, sunlight. Okay, so the light source irradiated the photocatalyst, electrons will excite. Okay, so electrons from here, will excite from the valence band and leave these protons, H plus, or simply we say as holes. Okay, so the electron holes. Okay, so the electron holes will react with water. Okay, since that we deal with this study, since that is a study dealing with wastewater, So it will react with the water environment to produce radicals, okay? These radicals through redox reactions, redox, reduction, and oxidation. So these radicals will attack, okay, and degrade the organic pollutants. The organic pollutants in this case is the BPA, okay? And it will convert them into harmless product, that is CO2 and water, okay? So here, what I would like to highlight here is the problem statement of what is the point of that initiate us to conduct this study. So I will address the remaining issues in the photocatalytic process in order to highlight the significant impact of employing the freestanding hollow nanofiber photocatalyst, okay, as the wastewater treatment solution. So as I mentioned earlier, endocrine disruptors, EDC, okay, such as BPA, it can interfere our body system by decreasing or increasing normal hormone levels, mimic the natural hormones, or alter the natural production of hormones. Okay, photocatalytic degradation can be utilized to oxidize BPA into carbon dioxide and water, as I mentioned in the mechanism process in the previous slide, right? So, and Digusab P25 TiO2. Digusab P25 TiO2 is the commercial photocatalyst that available in market now. That is mostly commonly used, yeah. So, however, many researchers have addressed the remaining issues with this photocatalyst, the TiO2, that are the wide band gap and a low surface area. So, these are the remaining problems or issues in the commercial TiO2 photocatalyst. Okay, so this has led to the development of hollow nanostructures photocatalyst. And one of them is hollow nanofibers, which offer a rather higher surface area, tunable bandgap energy, and superior photocatalytic performance. Okay, so however, the synthesis of hollow nanostructures often requires calcination treatment at very high temperature. So as a result, we obtain photocatalyst in powder form. But in our case now, it is in powder form, but it is a hollow nano fiber like structure. Okay, the fiber is in hollow nanofiber like structure. Okay, so powder form photocatalysts are often trapped in the effluent due to the very small size and causing low recyclability rate. So in return, this, sorry, I'm not feeling well today. In return, this impacts the overall photocatalytic performance due to the catalyst loss and might also increase the operational cost to separate the catalyst from the reaction medium, meaning that we have to have another or secondary separation process. Okay, so here we innovate a freestanding hollow nanofibers photocatalyst by assembling them via chemical treatment and vacuum filtration. Okay, it is capable to, so we believe, okay, it is capable to eliminate the catalyst loss and recyclability issue while maintaining the excellent degradation performance. This is based on our findings, okay, in which I will share later on. Okay, all right, so this is how we produce our hollow nanofiber. Okay, so as you can see in this figure, in our recent study, we managed to develop the freestanding TiO2 hollow nanofiber photocatalyst via the electrospinning. This is electrospinning, okay, assisted by template method. So this is the template method, okay, from here to through here, okay. So whereby the template or the sacrifice material that we use is PEN polymer, okay, PEN polymer, the polyacrylonitrile polymer. So firstly, we electrospin, okay, we electrospin. Change here. Okay, we electrospin the PEN template, okay, and get this solid nanofiber form. This is solid nanofiber form, right? So then we deposit the TiO2 salt gel that we prepared onto the PEN nanofiber by deep coating Okay, and finally, heat treatment by calcination above the degradation temperature of PAN. Okay, so that PAN will be burned off, and we get the TiO2 hollow nanofiber. Okay, very simple technique actually. And after we managed to get the TiO2 hollow nanofiber photocatalyst, we conduct some analysis on it. One of it is morphological analysis. Okay, so we vary in terms of calcination temperature from 400 degrees C up to 600 degrees C. Okay, 400, 500, and 600. So we name our sample is THNF 400. In this case, 400 degrees C. So THNF 400, titanium hollow nanofiber 400. Okay. So we studied how the change of the calcination temperatures affected the morphology of the produced hollow nanofiber. So starting at 400 degrees C, as you can see here, okay, from this figure, randomly aligned nonwoven nanofibers were formed, okay, with diameter of 240 nanometer, roughly about 240. Then this diameter was 46 nanometers smaller as compared to the original PAN template, as the heat effect caused the nanofibers to shrink. Okay. By the way, I'm sorry because my slides is a bit wordy because I just want while I'm talking so that you can extract as much as information from this content. Okay. Hope you're okay with that. Okay. So in figure A2 here. Okay. So we can observe the formation of boundary. So you can see here a clear boundary between the inner and the outer section of the hollow nanofibers. Okay, but no appearance of the hollow structures yet, right? So, in fact, at 400 degrees C, so please refer to this analysis, Tga analysis. At 400 degrees C, the PAN template has started to melt and disintegrate. Okay, but then we can conclude that a 400 degrees C was not enough for the completion removal of PAN to form hollow nanofibers. So you can see still there are remaining compounds of PAN in the analysis shown here. Okay, at 400 degrees C. Okay. Okay. Now the morphological analysis on the THNF 500 degrees C. Okay. So we increase up to now we increase to 500 degrees C. So compared to THNF 400, the nanofibers were much shorter. So as you can see here, okay, shorter due to higher temperature. Okay, as we can see from the TGA curve here, so the weight of nanofibers decreased significantly. Okay, decreased significantly at 500 degrees C, which means the majority of the PAN and organic components had been eliminated. Okay, accordingly, we can already see the appearance of hollow cavities here. Okay, but with agglomerated nanofiber strands. Okay. All right. Now, THNF 600 at 600 degrees C of calcination temperature. Okay, and as you can see, at this temperature, the surface of nanofiber. Take a look at this figure. So you can see here, very different, yeah, from here and here. Okay, the surface of the nanofiber itself rougher. Okay, yeah, very significant. Okay, rougher than the THNF 500, right? So the rough surface of THNF 600 is an advantageous for photocatalytic applications because it provides more active sites for pollutants absorption and UV irradiation. Okay, it is like blessing in disguise, something like that. You obtained not really a smooth surface of the nanofiber, but you obtained rough, but it can provide you this this advantage in order to provide more active sites for pollutants absorption and UV irradiation, in which later on it will increase the enhance the performance of the degradation of the BPA or any pollutants. Okay, so in figure C2, here, okay, there are more visible hollow cavities in the core of the nanofibers, right? So the synthesis of TiO2 hollow nanofibers is strongly dependent on PAN decomposition. Okay, so here you can see here the synthesis, therefore the ideal temperature for forming TiO2 hollow nanofibers is we take as 600 degrees C. So all of the components had been removed completely. Okay, and I can say that as compared to THNF 400 and 500, we have considerably well interconnected nanofibers. Okay, so we actually it has no point to further increase the temperature in order to maybe to improve the hollow cavities or hollow nanostructure visibility. Okay, because this will increase the energy requirement and it will not cost effective anymore, right? So we stop at 600 degrees C and take this 600 degrees C or THNF 600 to be considered in the following analysis. Okay, so in photocatalytic degradation process, the surface area of the photocatalyst is very important, okay, as it also affects the UV absorption and reactant surface absorption, right? So we can see that both the specific area and pore volume of the THNF increase, okay, as the calcination temperature increase. Okay, so the relatively low specific surface area and pore volume THNF 400, okay, can be attributed to the melting of PAN component, which might have covered and blocked the existing pores of nanofibers. Okay, so as the temperature increased, okay, the hollow structures were more prominent and the surface of the nanofibers were rougher. So these conditions provide a greater accessibility surface for nitrogen absorption. So in this case, in this analysis, yes, it is for nitrogen absorption, okay, but with this high surface, specific surface area and specific pore volume, this reflect the absorption, high absorption of the UV and also the pollutants. Okay. Okay, so based on this is the phase analysis of our photocatalyst. So based on the XRD patterns here, okay, all samples were identified as crystalline. Okay, so all the peaks detected in THNF 400 here, the A, okay, figure A, okay, were ascribed to anatase TiO2. So we based on the open literature. So these are the peaks for anatase TiO2. Okay, some rutile TiO2 begins to develop in THNF 500 here. Okay, okay, THNF 500 as some weak rutile peaks started to emerge. Okay, here as shown in the bold diagram here, okay, like a 27.4 degree, 36.0 degree, and 68.7 degree. So THNF 500, after we make a simple calculation, it contains of 82.1% anatase and 17.9% of rutile. Okay, so the appearance of additional rutile peaks and sharper here, and intensified existing peaks indicated the majority of THNF 600 was rutile. Okay, so THNF was made up of 75.8% of rutile and 24.2% of anatase. Okay, so the calcination temperature has a significant influence on the phase conversion from anatase to rutile. So heat treatment causes, so please take a look at this transformation mechanism of the anatase to rutile. Okay, so the heat treatment has causes the octahedral TiO2 to deform, resulting in the breaking and reformation of new TiO bonds, at the grain interface and interior. Okay, so oxygen vacancies were created as a result of bond breakage and lattice deformation. Okay, so the oxygen vacancies act as a nucleation site facilitating the rutile phase to develop. Okay, so we can see later on how phase analysis is very much important in photocatalytic reaction. Okay, why we want to have more rutile rather than anatase. Okay. Okay, then we use UV spectrophotometer to assess the optical properties of the photocatalyst. So the absorption age of THNF 400, 500, and 600 were found to be approximately here. You can see here the tangent line of each of the spectra. Okay, is 381, 400, 422 nanometer respectively. Okay, so the enhanced absorption might be attributed to the presence of rutile content. Okay, so the rutile itself has a narrower band gap in which it is 3.0 electron volt than the pristine anatase phase 3.2 electron volt. Okay, so the Welcome function was used to calculate the photocatalyst band gap. Okay, the band gap energy was observed to drop as the calcination temperature increased from 3.5.0 to 3.0 electron volt. So meaning that as the calcination temperature increased up to 600 degrees C, we managed to get 3.0 electron volt of band gap. Okay, so this finding suggests that THNF 600 has superior optical properties over THNF 400 and THNF 500. Okay, so the band gap narrowing was attributed to the increased fraction of rutile. So theoretically, please take a look at this figure. Rutile TiO2 is denser, 9% than anatase TiO2 because the Ti distance, you can see here the Ti distance in rutile is shorter. So you can see the angle is very significant difference between the anatase TiO2 and rutile TiO2. So as a result, the orbital localization of the Ti3d and O2p has become more pronounced, okay, resulting in a narrower band gap. Okay, so this narrowing band gap is very crucial in photocatalytic process in enhancing the active sites for light irradiation. And in fact, we can use low cost or even free visible light, such as solar light for irradiation. So we want to have as low as we can for the band gap of the photocatalyst. Okay. All right. So now this is the photocatalytic BPA degradation activity. Okay, in which it comprised of the absorption and also the degradation process. Okay, so these are the activities involved in a photocatalytic degradation process. So all these synthesized THNF 400, 500, and 600, and also the Dilusa P25 TiO2, the commercial TiO2 we use in the photo degradation of BPA. Okay, as control, we conduct the photolysis experiment. Okay, we conduct in the dark environment. So the result was insignificant, just less than 1% of degradation of the BPA. So which implies that the photodegradation of BPA was subjected to the presence of TiO2 photocatalyst. So meaning that we have to include the photocatalyst in order to have the photocatalytic degradation activities on the BPA. Okay. So overall, the degradation efficiency of THNF 600. Okay, as you can see, this one. Okay, the green line, okay, outperformed than the others at 71.48%. which is 85% higher than that of P25, TiO2 P25. So the comparably excellent degradation performance of THNF 600 might be explained or suggested by, firstly, a larger surface area for BPA absorption and UV light absorption. As mentioned before, the existence of hollow structures increase the specific surface area as compared to the Gusa P25. So it allows more photon energy to be absorbed in order to generate charge carriers for BPA degradation. Okay. Then secondly, optimal heterojunction of anatase and rutile. Okay, this is where the phase analysis is very much important in photocatalytic degradation activity. So the optimal anatase-rutile ratio has not only lead to band gap narrowing, but also suppress the electron hole recombination. Okay, so please take a look at this figure, in which it shows the mechanism of the photocatalytic degradation. This one is for the TiO2 P25, and this one is our photocatalyst THNF 600, in which you can see clearly, you can see the combination, or we have the biphasic heterojunction of rutile and anatase. Okay, so thirdly is the light scattering effect. So this is how the scattering light effect in the hollow nanofibers cavities. Okay, right. So in figure here, when the irradiated UV light penetrates the hollow structured THNF 600, the incident light is scattered within the interior of the THNF 600 and causes secondary absorption of the scattered light, leading to light harvesting enhancement. Okay, right. Okay, and now actually, okay, this one is very important. Okay, to determine the optimum catalyst dosage. Okay, for the development of freestanding hollow nanofiber later on. Okay, after we select THNF 600, okay, we study the effect of the catalyst dosage, so that we can choose at what dosage of the catalyst we can use to produce the freestanding hollow nanofiber film later on. Okay, so the dosage of photocatalyst was investigated in the range of 0.25, okay, 0.25 to 1 gram per liter for the degradation of BPA using THNF 600. Okay, so the increase of the THNF 600 dosage also increased the photo degradation of BPA. So as you can see here, yeah, and it was maximum at 0.75 gram per liter here. So the increase in degradation efficiency is explained by the increase in the number of active sites of the THNF 600. Okay, so active sites provides the surface for UV light irradiation, which initiates the electron excitation to generate hydroxyl radicals. Okay, so therefore more BPA molecules could be mineralized into CO2 and water. So actually I keep on explaining the same thing as if you realize it is a really how can I say, very same explanation as I discussed about the mechanism of the photocatalytic process itself, right? Okay, it just we change the keyword of the photocatalyst and also the pollutant, right? So beyond, as you can see here, beyond 0.75 gram per liter, okay, the degradation efficiency decreased significantly. So this one, okay, as you can see, if you compare between 0.75 and also 1 gram per liter. Okay, this is because actually the dispersion of high amount of THNF in BPA solution itself. So as you can see here in the figure B here, okay, right? As we can see, the BPA solution turn turbid, okay, turn turbid and cloudy with increasing photocatalyst amount. So which could be the possible cause of the decreasing degradation, okay, cloudy. So it caused the light scattering effect where UV irradiation could not reach the active sites of the THNF. Okay, thus reduce the photocatalytic activity. So therefore, we take 0.75 gram per liter as the optimum dosage. Okay. All right. So this is the procedure on how we produce our freestanding TiO2 hollow nanofibers. So we develop using 0.75 and we compare with 0.5 gram of the THNF 600. Okay. So THNF, firstly, THNF 600 was dispersed in ethanol under ultrasonication. Then the solution was poured into the filter funnel. Okay, this is the filter funnel with an inner diameter of 4 cm. After 15 minutes of filtration, the obtained freestanding TiO2 hollow nanofibers was dried for 24 hours before we peeling off from the filter paper. Okay, after being peeling off, the THNF 600 on the FS75, we call as we named as FS75 flat sheet 75. It's reflecting the dosage of the TiO2 in which 0.75. So we use FS75 THNF a sheet adheres strongly and no wrinkles or cracking or chipping here. You can see. Okay. With reduce the amount of THNF 600 to 0.5 gram per liter, the surface of the photocatalyst tend to crack. As you can see clearly, you can see here it cracked and when we peel off from the filter paper. So with less amount of THNF 600, the nanofibers were loosely assembled and inadequately adhered. So causing the FS50 THNF to chip and break into smaller pieces. Okay. So here, this is the recyclability study of the freestanding TiO2 hollow nanofibers. We compare the THNF 600, okay, and the flat sheet 75 THNF in terms of recyclability. So the weight of a catalyst used was measured prior to every cycle. So we have 5 cycles. During the first cycle, the degradation efficiency of THNF was slightly higher than that of FS75, as you can see here. Okay, here, right? Despite having the same weight of catalyst, okay, 0.75. Okay, so this slight difference is caused by the stacking of the photocatalyst in FS75, okay, which may hinder some of the active surface areas. A significant decline, okay, significant decline in the weight and degradation efficiency of THNF 600 can be observed in the following cycles 2, 3, 4, and 5. Although catalyst recovery has been done through centrifugation, so the THNF 600 still has low catalyst recovery due to its very minute size. Okay, so I'm talking about the THNF 600 in powder form. Okay, right? On the other hand, the catalyst recyclability of the FS75, okay, was significantly improved even after 5 cycles of reaction. With the increasing number of cycles, the degradation of BPA was only reduced by 5% on average. Okay, so freestanding THNF is very promising because of the fissile synthesis method, excellent recyclability, does not require catalyst recovery and regeneration process, and can reduce operational time and cost. Okay. In fact, okay, for the regeneration or when we want to take out the FS75 for first actually from first cycle until third cycles, we managed to take it out by using tweezer. Okay, but unfortunately, after 4 cycles and 5 cycles, we have to also collect it using the centrifugation. Okay. Okay. Here I just would like to share one of the photocatalytic reactor that have been developed by Panasonic. Okay. But actually it is still a prototype. Okay, it is still a prototype. So actually, we can develop this kind of reactor for water and wastewater treatment very soon. Okay, actually, what we have in our lab is more or less about the same, but just in bench scale. Okay, so I come to the conclusion and future outlook. Okay, first, the development of hollow nanofibers and freestanding photocatalysts can synergistically mitigate the remaining issues in photocatalytic field, in which I have discussed in earlier of my presentation. And then the freestanding hollow nanofiber can be further improved by doing more characterization studies such as system and mechanical tests. Okay, but then in terms of mechanical tests, as I mentioned just now, we managed to collect the freestanding PiO2 hollow nanofiber, okay, by using tweezer. So it's still in its current form, and the loss of the photocatalyst is just about 5% throughout the cycles. Okay, so that is one of the indicator to show that our photocatalyst is still in its form, and it is stable in terms of its mechanical stability. Okay, so we have to do this. Actually, we are doing it, okay, for the FreeSam in the mechanical test on the freestanding hollow nanofibers. Okay, and last but not least, freestanding hollow nanofiber is yet to be commercialized, but the potential is very huge. Okay, and as you can see here, we can use or we can have this type of photocatalytic reactor by using our own photocatalyst developed in our lab. Okay, so as for that, thank you very much for your kind attention. I pass over this session to the moderator. Thank you very much.
Thank you very much for Dr. Juhana for delivering your amazing speech about freestanding hollow nanofiber. I think it is promising material for photocatalyst. Okay, we move on to the next speech. We have also another amazing speaker from Japan, Dr. Sadaki Samitsu. He is now a principal researcher in Data-Driven Polymer Design Group, Research and Services Division of Materials Data and Integrated System, National Institute for Material Science, NIMS. He also, as a guest professor at Department of Nanoscience and Nanoengineering, Faculty of Science and Engineering, Waseda University. He graduated from the University of Tokyo, so he finished his PS in Faculty of Engineering, specifically in Applied Physics in 2006, and also in MS, Graduate School of Frontier Science in Advanced Materials Science, and doctoral course of Graduate School of Engineering in Applied Physics, and the last PhD Engineering from the University of Tokyo under supervision of Professor Kozo Ito. He also received abundance of awards. For example, in 2018, he received Publicity Award from a publicity committee in 67 SPSJ annual meeting. In 2017, he is a Young Scientist Presentation Award in 63rd Polymer Research Meeting. In 2015, he received Young Scientist Prize or Silver Medal from Minister of Education, Culture, Sport, Science and Technology, MEXT. And also in 2015, he also got NIMS President Award for Young Scientists. And many words that I cannot read one by one, followed by abundant high impact factor publication. He also conducted major research projects that worth more than 100 million yen Japan, collaborating with many industries, research institution, and many more. And today we are delighted to hear some talks from him about nanoporous polymer for photocatalytic application. So here he is, the second speaker, Professor Dr. Sadaki Samitsu.
Thank you very much, Chairman, for very kind introduction. So my name is Sadaki Samitsu from National Institute of Material Science. So I will share with my presentation. Can you see my presentation?
Yes.
Okay. So I will today I will talk about. So first of all, it's my great honor for inviting me this great excellent meeting. I would like to appreciate all the committee members and all the related researchers. So today I will talk about the fabrication of the nanoporous polymers for photocatalytic applications. So here is my research on the nanoporous polymers, including the fabrication, characterization, and application. So there is a selected application of published in the several papers. So, but due to the limitation of the presentation, today I will focus on the fabrication method. So nanoporous polymers are strongly demanded for global issues in energy, environmental, and medical application. So the various fabrication methods have been reported in top journals like Science and Nature Materials, as well as Nature Nanotechnology. There are various types of fabrication methods, but among them, the phase separation is the mainstream for the practical usage. This is today's topic. Because the phase separation is very simple. And here is a general scheme of the phase separation method for making porous polymers. First, we prepare a uniform polymer solution and produce phase separation structure as shown here. And these are published in Nature Material or Science. However, they have a limitation because they give only macropores larger than the 10 micrometers, and the small area is small. So my concept is to decrease the solvent crystal down to the nanometer and form a mesopore. So based on the theory of the crystallization step includes two steps. First is a nucleation, then crystal growth. So crystallization theory gives this temperature dependence. So crystal nucleation rate of the crystal that drastically increase with decreasing temperature, and the crystal growth rate decreasing with decreasing temperature. That means at low crystallization at low temperature gives a high nucleation density as well as a slow growth rate. That is very favorable for this solvent nanocrystal. So this is my idea. So procedure of this fresh freezing method is applicable to various types of the commercially available polymers. And the polymer prepare and several events like dimethyl formate. polymers initially quickly freeze in liquid nitrogen and give a glassy state of the polymer solution. Then nanocrystallization proceeds at low temperature, such as -80 degrees in a refrigerator. Then solvent exchange also proceed at low temperature to maintain this phase separation structure. And I usually use a methanol. These are poor solvent of these polymers. And then finally, I dry the sample at room temperature and get this type of the non-porous materials. You can see the same transparent appearance of the material due to the uniform nanopores. Here is a SEM image of the Mesoporous Polystyrene obtained from the 40 weight % in dimethylbromide solution. Scale by is a 100 nanometer, and you can see the very large numbers of the mesopores. This pore size distribution can be quantitatively determined by the nitrogen gas adsorption method using this instrument, and they gave the peaks at 15 nanometer and very narrow distribution, like 8 nanometer in difference. So they have a very uniform pore size and large pore volume of the mesopore. Is the concentration. Pore size drastically decreased to the 98 nanometer to 15 nanometer. I don't explain the detail of the mechanism in here, but this is governed by the phase diagram of polymer solution. So higher initial concentration gives smaller mesopores. So this method is applicable to various types of the commodity polymers, including engineered plastics such as polysulfone, polyethyl sulfone, or commodity polymers such as polycarbonate, polystyrene, polyacrylic nitrate, and polyvinyl chloride, and other engineering plastic. Actually, the engineered plastic improves the thermal stability and mechanical strength of the mesopores, so they are very promising for practical applications. So wait. Yes. So here is a video of the one-step fabrication of the mesoporous polymers. Actually, the direct spinning of the polymer solution into a low temperature methanol bath gives a one-step fabrication of the mesoporous polymers like this. Here is a polymer solution, and the polymer solution injected in the cold methanol, and they give us such a fiber structure of the mesoporous polymers. So this method also gives a hierarchical polar structure, such as also the mesoporous polymer is applicable to form the hybrid material. So just prepare a polymer solution and add the nanoparticle and do a nanocrystallization, and you will get a hybrid material of the nanoparticle and nanoporous polymers. So this is direct applicable to the photocatalytic application. You can combine this method to a photocatalytic nanomaterial. So, and also this method gives a very unique material shape, such as a sheet, fiber, or pellet. And these are very useful for the separation and purification applications. Sheet form gives a 90% removal of the 5 nanometer colloids with high water flux, and the fiber and pellet structure gives a molecular adsorbent for dissolving oils. As a short summary, I introduced a nanocrystallization method called flash freezing to fabricate a nanoporous polymer from commodity polymers with large specific surface area and uniform pore size to 10 to 100 nanometer. they give a form nanoparticle hybrid and with various material shapes. And they are promising for separation and purification applications. So now I move to the second topic. This topic relates to the polymer crystallization. A gel precursor method for robust mesoporous monoliths published in the Macromolecule in 2018. So background of research is a physical generation of polymer crystallization. As you know, the crystalline polymers are used for the membrane fabrication called thermally induced phase separation. But still there are challenges for the thermal and mechanical stability of the membrane because these polymers are not so stable for such conditions. In that viewpoint, engineering plastic is very promising because they are they have high thermal stability and mechanical strength. But limitation is that crystallization is due to the high glass transition temperature and low regularity. And only a few polymers is reported to cause a physical generation. So in the detailed material exploration, I found the polyethyl sulfone polymer of a type of the polymer of the super engineering plastic can be crystallized. I found this can be crystallized in a solution. And these are commercially available and used for the filtration membrane. And so solvent-induced crystallization of engineered plastic is my idea. So experimental procedure is also very simple. Just dissolve the polyethyl sulfone in the dimethyl hormoamide or mixed with benzene. And the concentration is 10 to 38%. And dissolved at high temperature gives a uniform polymer solution. And store at room temperature causes physical generation. And removing the solvent from this physical gel by washing with methanol and vacuum drying, then you can get a mesoporous polyethyl sulfone. And here is a cross section of the SCA image of this monolith. And they give the 10 to 20 nanometer nanofiber and 5 to 100 nanometer pores. And the mechanism of this physical generation is confirmed by the X-ray diffraction pattern. In the gel, we can see the very clear peaks. That means they form some kind of the crystal in the gel. So the polar structure is controlled by the gelation condition, controlled by the solvent ratio or concentration of the polymers like this. And also that material gives a very high thermal stability of mesoporous due to the high glass transition temperature of polyethyl sulfone. And even at high 150 degrees for over 60 hours, they maintain most of the mesoporous. So such porous material is promising as a flexible thermal insulator. This crystallization of polymers also gives the various type of the material shape like microparticle. This one is a polyethyl sulfone microparticle having the nanoporous structure. And this material can be obtained by the designing the processing condition like a solvent type. And this material, this particle has a 7 nanometer pores. And also the particle size is around 1 to 3 micrometer. And surface area is over 200 square meter per gram and promising as a support of the porous photocatalytic nanomaterial. So here is a summary of my research. Here today I introduce two methods. It's the solvent crystallization and polymer crystallization. and flash freezing non-precization is reported in Nature Communication, and gel precursor method is reported in Macromolecules. So in conclusion, the advanced fabrication methods plays a key role on the performance improvement of the photocatalytic application. So I expect all the research focusing on the new fabrication method of the porous polymers. So actually, now I'm a member of the Department of Non-Science and Non-Engineering in Waseda University from this April. So actually, I have a recruitment for the students, like student internship in NIMS for maximum 3 months, and a PhD student in the Waseda University. So if you have an interest, please contact me freely by email. So finally, I would like to acknowledge from the Japanese government for financial support and all my collaborators in NIMS, as well as the other universities. Thank you for your much kind attention.
Thank you very much, Professor Sadaki Samitsu. I think that's the full information is very interesting. And for attendees today who wants to join your lab, maybe can send you an email after this.
Thank you.
Thank you so much. And we will move on to the third speech. And the third speech will be delivered by Dr. Muhammad Azuwa Mohamed. So I will introduce him first. He is a senior lecturer and also head of catalysis for renewable energy and environmental sustainability research cluster in Department of Chemical Science, Faculty of Science and Technology, Universiti Kebangsaan Malaysia. And also he is part of research fellow in Polymer Research Center, Universiti Kebangsaan Malaysia, and also associate research fellow in Fuel Cell Institute, Universiti Kebangsaan Malaysia. He pursued his Bachelor of Science in Industrial Chemistry as a second-class honors upper division in Department of Chemistry, Institut Teknologi Malaysia, and Master of Engineering in Gas with Best Student Award and Pro-Chancellor Award in Universiti Teknologi Malaysia, and also Doctor of Philosophy in Hydrogen Energy with Doctorate Golden Award in Fuel Cell Institute in the National University of Malaysia with a specific project Biotemplated Inspired Tailoring Core Cell C-Doped GC 3 and 4 based metal oxide heterojunction photocatalyst for solar fuel generation. And he also received abundant of awards, so I will mention several of them. In 2020, being listed among world top 2% scientists 2020-2021 database by Elsevier Stanford University. And also in the same year, Tan Sri Dato Ongki Hui Postgraduate Chemistry Medal 2021, Malaysian Institute of Chemistry. Also in this year, Doctorate Golden Award 48 UKM Convocation 2021. And last year in 2020, he is being listed among world top 2% scientists in 2019, database by Elsevier BP Stanford University. He has research interest in photocatalysis, photoelectrocatalysis, or catalysis in membrane technology, renewable energy, multifunctional material chemistry, and waste utilization. Since September 2014 until July 2020, he achieved highest citation of a single paper for 107, with total citation 1,608. He also got his its index about 24. He also has a granted patent in method of preparing biotemplated carbon doped gravitic carbon nitride. Without further ado, I will give you the time and the screen. Please, Dr. Muhammad Azuwa Mohamed.
All right, thank you so much, everybody. All right, first of all, I would like to thank the organizer for organizing this very nice meeting. So today, basically it is for sharing session. So I do hope that what I'm sharing today can give you some idea or a research interest for future research, for applying grants maybe, or publishing in high impact journals, all right? Okay, so as you know, today I'm going to share with you regarding the topic photocatalytic membrane for renewable energy and wastewater treatment. All right, so you already know my name. My name is Dr. Muhammad Azuwa, okay, from Universiti Kebangsaan, Malaysia. Okay. I'm sorry. Okay, so right, so this is the current issue. So when we talk about photocatalysts, is actually have been inspired by our nature. Okay, so our plant. All right, so photocatalysts has been mimic this kind of the process. And then artificial photosynthesis is very, very promising, green and clean technology. Okay, so what we can do from this technology is that we can obtain renewable energy such as hydrogen from the water splitting, and then we also can reduce carbon dioxide in our atmosphere into solar fuel. Okay, so we also can produce polymer chemicals based on this technology, and then we can also use for various kind of application. Yeah. All right. I'm sorry. Okay, so photocatalysis is widely used for hydrogen production, CO2 photo reduction, as well as organic contaminants in water or wastewater, or in a gas phase. Okay, so what is the current trend? So this is current trend. Maybe you might also interested to explore more about this, right? So the current trend of photocatalysis development is we are looking for earth abundant materials. Okay, so it's low cost in terms of material and also processing, and then that particular material must be stable, high stable as possible for long run reaction time, and then high efficiency for broad solar light spectrum harvesting, and then excellent photo generated whole separation efficiency. All right, so if you can see from this figure, this is an example of a band gap structure of photocatalysts. Okay, it consists of a valence band, which is VB, and conduction band is CB. All right, so normally when this material absorb light, so the electron from the valence band will be excited to the conduction band. So that leaving positive hole at the valence band. So the positive hole can consider as an oxidation site, whereby at the conduction band, which is rich of electron, can be used as a reduction site. Okay, so the reduction site can be used for water splitting application, and then we can use for CO2 reduction and so on. Right, so if you can see from there, we can see this is a very versatile material. We can have a various application in one materials. Okay. All right, so this is example, a list of developed photocatalysts in this world, yeah, by scientists all over the world. Okay, so basically, the band gap of each of the photocatalysts to be applicable with a specific reaction, those band gap must be straddled between this chemical potential, which is over potential, for certain reaction. Okay, for in this case, if you can see from there, if the on the top one is we call as a valence band, and the bottom one is the bottom one is the valence band, and the top one is conduction band. So if you want to make sure that we are designing a catalyst can be utilized for all the reaction, so meaning that if you want to produce hydrogen, to reduce CO2, and then to be used as the photo degradation or for wastewater treatment, the band gap must be within this over potential of a certain reaction. Okay. All right. So this is I would like to introduce what I'm doing for the past 5 years. Okay. Basically, what I'm trying to explore is a graphitic carbon nitride as a new class of photocatalytic material. So since 2009, yeah, Wang and his co-worker proved the feasibility of graphitic carbon nitride, okay, to be applied as a non-metal visible light photocatalyst for photocatalytic hydrogen evolution. Okay, since then, we have a lot of publication and report on the literature on this this material development. Okay, so why this is a very interesting materials among scientists all over the world? Because of what? Because it is easy to prepare by using a thermal condensation method, and then a low-cost precursor. For example, we can use it. We can obtain this kind of material from urea, thiourea, melamine, and so on. All right. So basically, they have. We need to do a thermal condensation at certain temperature. Okay, to obtain graphitic carbon nitride. All right. So one of the important properties, yeah, for this material, because why people are very interested to research more about this, because of the tunable band gap structure. Okay, so has been explained by Dr. Juhana Jaafar just now. Previously, he mentioned that she mentioned that titanium dioxide, yeah, we have a band gap around 3.2 electron volt, which is only can activate under UV irradiation. So to make use of full solar irradiation energy. Okay, so most of the researcher tend to narrow down the band gap, okay, around 1.8 to 2.7 electron volt to harvesting more visible light, okay, which is from wavelength 460 to 698 nanometer. Okay, so for your information, this region actually consists of 49% of solar energy. Okay, so solar light, solar irradiation. So it's very high. So as compared to UV light, UV portion in the solar is around 5% only. So that's why instead of we using 5%, why not we go for 49%? Okay. All right, so this is the band gap structure of graphitic carbon nitride. So what is the advantage? Okay, first is strong reduction ability, active invisible light, abundance, easy fabrication, 2D layered structure, non-toxicity, challenges that we need to take action to overcome this. So in order to make sure that this material, which is very low cost material, can be applied in our daily life, for example, okay, for more practical and towards commercialization. We are pushing this material toward, okay. All right. So because of that particular drawbacks, okay, of the graphitic carbon nitride, so my team have developed one of the approach in order to minimizing the negative side of the graphic carbon nitride. So, for example, we use biotemplate synthesis to produce graphic carbon nitride. Okay, why we use biotemplate? Because it is self-assembled characteristic. Okay, it's low cost, green, and sustainable synthesis system, and this is a bonus. Yeah. Provide in situ carbon doping for enhancement solar harvesting. Okay, so why carbon doping? Because this is what we call is elemental doping to the photocatalyst in order to lower or narrowing the band gap of the photocatalyst. All right. So this is very, what we call it, is very interesting approach to be considered in order to prepare a photocatalyst. Even in graphite carbon dioxide or metal oxide, metal sulfide, metal phosphate, and so on. So we can use this kind of method to produce photocatalyst. Okay. All right. So my theme before focusing on the cellulosic material as a biotemplate. Okay, so to be specific, we use a carpet fiber. Okay, normally this carpet fiber used for pillows, padding pillows, and mattress sometimes, right? So we use this because this carpet fiber have high content on cellulose. Okay, so cellulose is the the main composition of the carpet fiber, and then apart from that, this kind of fiber is very unique, yeah, in terms of morphology. If you can see from the same image, you can see that the carpet fiber naturally is hollow fiber, microtubular structure. So we are trying to mimic this kind of structure to obtain the catalyst that we want. Okay, all right. So, so we did successfully prepare graphite carbon dioxide microtubular derived from carpet fiber. All right, you can see before and after. With and without a biotemplate, you can see the pore structure of a graphite carbon dioxide become more prominent, which is very good. Okay, and then it's a bit more thinner and then high porosity. And then this tubular structure improves light scattering and absorption for the photocatalysis to absorb light for the formation of generated electron hole and also amount of hydrogen produced based on this material. Okay, so we also did some test with another metal oxide, for example, zinc oxide. Same goes to zinc oxide. The combination of heterojunction photocatalyst enhance the catalytic properties of the materials. Okay, so if you can see from this image, we can see that without carpet fiber, the zinc oxide is like in the nanorod structure. But with the carpet fiber as a biotemplate, we can have a very interesting structure of the photocatalyst. Okay, why? Because of the carpet fiber assisting the zinc oxide in terms of growth and formation. All right. Okay, so the photocatalyst, the membrane, the photocatalyst with the membrane. Okay. All right. Okay, so apart from that, this is quite a new thing, yeah, regarding the photocatalytic membrane as compared to other membrane, photocatalytic membrane. Even though the presence of the photocatalyst within the membrane can, slightly improve the falling, anti-falling properties. However, but sometimes the photocatalyst maybe can be deactivated, okay, due to not stable material that we choose from. Okay, that's why choosing the right material for this application is very necessary. Okay. Okay, so solar fuel generation. Okay, so basically a solar fuel is a synthetic chemical fuel produced from solar energy. Okay, light is used an energy source with solar energy being transduced to chemical energy, typically by reducing proton to hydrogen or carbon dioxide to organic compound. So why solar fuel? Because of hydrogen can be used in a fuel cell, hydrogen fuel cell. Right, so the product from photo reduction of carbon dioxide can be used for another fuel cell. For example, if we produce methanol from carbon dioxide, that methanol can be used in direct methanol fuel cell, and so on. All right, so basically how we do, we obtain this solar fuel. So we can obtain in terms of two setup. First, in particulate system and also photoelectrochemical cell. Okay, so we have two options here. Okay. All right, so this is the example of typical photoelectrochemical cells that common in use to produce hydrogen and also CO2 reduction. Yeah, so if you can see from there, we have photoanode, photocathode for the cell. So and in the middle we have polyelectrolyte membrane. So this membrane is very important in order to conduct proton that generated from the anode side to the cathode side. Okay, because of why? Because the photo-generated electron from the photoanode it will be transferred, transferred to photocathode, and then this electron will react with the proton that have been transferred by the membrane. Okay, so depending how much electron that we produce, we can have a selective or various product based on this particular reaction. Okay. All right. So in a PEC cell, we have several types. Okay, we have several state. For this one is a liquid state, like I mentioned previous slide. It's also in terms of liquid state. Okay, so this is very popular among scientists around this area, using solid liquid state PEC cell in order to use for hydrogen generation, CO2 reduction, and also wastewater treatment. Okay, so normally the use of membrane is required in the setup. Okay, so the membrane that become a center of the system. All right, so this is a solid state PEC cell. Okay, so normally solid state we use a vapor or gas phase condition to have reaction to be a certain reaction. For example, water splitting for hydrogen generation, CO2 reduction for various solar fuel production, and then photoelectrodegradation for wastewater treatment. What is the advantage of using this? Okay, so basically, like country that have have a desert side, so they have no water resources mostly. So the production of energy based on water splitting can be beneficial for that area. Why? The vapor, we got the water vapor, and then to purge into the system, and then the system will what we call it, do the reaction, and then to split water into hydrogen and oxygen. So they can use hydrogen for their fuel cell, okay, hydrogen fuel cell and so on. All right. Apart from that, we also can produce solar fuel like methanol, methane, ethane from the CO2 reduction by using this kind of a sample or setup. Another advantage is that we can minimize the formation of bubbles and operation costs required for pumping liquid water or other liquid because of the natural air is convection itself, yeah, in order to supply water vapor. Apart from that, when we talk about hydrogen generation from sea, from seawater, we did not have requirement to remove salt from the impurity in seawater. So this is very promising setup, but still it's depending in what you want to do. What are your target reaction? Okay, we can focus based on a certain reaction that I have mentioned before. All right. So currently, what we are doing is that we are trying to incorporate the photocatalyst within the photoelectrolyte membrane. Okay, so while we have a motivation to produce a more compact device as compared to the PEC cell setup that I mentioned before. Okay, so it's much more compact, where the photocatalyst on top of the membrane. Okay, so this is very beneficial in terms of improved proton transport mechanism and promoting simultaneous reaction between photo-induced electron for efficient photoreduction reaction. For example, for hydrogen generation, because of the H+, which is proton, is reacted with the electron produced by the photocatalyst, can be reacted simultaneously to produce hydrogen and to reduce CO2 and so on. Okay, what are the strategies? So basically, we immerse the pore of photocatalyst with different proton carrier, and then we do surface functionalization of photocatalyst with different functional group like mentioned here to enhance acidity and hydrophilicity. So the mechanism of proton transportation within the membrane can be enhanced, as well as simultaneous reaction with the electron that have been generated by the photocatalyst. Okay, this is very, but this is actually ongoing research in my lab. I don't have some certain data here, but this is the thing that you might can explore at your university, so we can collaborate about this kind of research in the future. All right. Okay, as a summary, integration of photocatalysts and also membrane technology is very important in order to minimize issues that related to the global warming, fossil resources depletion, environmental pollution, and so on. Right. To base of my knowledge, to the best of my knowledge, I do believe that low-cost synthesis fabrication route of photocatalytic membrane with efficient solar harvesting, efficient separation behavior, excellent hole separation, stable and durable photocatalysts become a very crucial requirement for practical application and commercialization. This is our main challenge. Okay, so what we are facing for. All right, so apart from that, in-depth understanding or synergistic interaction between the photocatalyst and the membrane can be more enlightened by systematic experiment and quantum theoretical simulation or modeling. Okay. All right. Apart from that, accomplishing the United Nations Agenda 2030 for Sustainable Development demand dedication for all parties, which is us, scientists all over the world, and then our government supporting our research, okay, by executing integrated process at all levels and region. Okay, so as a scientist, it's not a very simple task to do, but we have a lot of things need to think about. And yeah, I think that's all from me. I do hope that we can have research collaboration in future, inshallah. Thank you so much.
Okay, thank you so much, Dr. Azuwa. So actually your spirit pushed me to do a better. Okay.
Recording in progress.
Chemical and Natural Resources Engineering, Universiti Malaysia, Pahang. Her passion and dedication towards her research are reflected in her numerous scientific national revered.
And a very good morning. Is my voice clear?
Clear.
Okay. Thank you. Okay, thank you, Dr. Gusti Uminia, for your kind introduction. So again, my name is Dr. Farhana Aziz. I'm a senior lecturer from School of Chemical and Energy Engineering, Institut Teknologi Malaysia, and also Associate Research Fellow of Advanced Membrane Technology Research Center, Institut Teknologi Malaysia. So as you can see on the screen, the title for my presentation today is Advanced Photocatalyst Material for Wastewater Treatment. I will be focusing on the heterojunction photocatalyst. So my topic is a bit different from others because I'm not talking about the membrane. So I will be focusing only on the photocatalyst itself. So I will just talk about the heterojunction photocatalyst. Okay, this is the presentation outline. So I will start the presentation with brief introductions about the photocatalyst and also the recent research trends in the photocatalysis. Then we'll talk about the heterojunction, on the types of heterojunction, and then I will share with you all my recent research on the heterojunction photocatalyst. So we have prepared two types, which is PNP heterojunction and also direct Z scheme heterojunction, and finally the conclusions. So there is a quote that says, "Be a photocatalyst for change." So photocatalyst, in my opinion, and I believe from other speaker opinion, is a very interesting material. Why? Because this material will change its surrounding when it come in contact with sunlight or artificial light. So this figure, I would like to share with you the distributions of photocatalyst publications based on major sub-theme. And this publication is within 2010 until 2020. So I would like to highlight that the size of nodes. So I want to share with you the size of node. So let me use the laser pointer. Okay, so the size of node, for example, the visible light radiation. So the size of node is proportional to the frequency of the document associated with the keyword. So that is the larger nodes represent the most widely researched themes or topic. So as you can see, the visible light irradiation is among the most recent trend in photocatalysis. And if you look closely, you will see the linkages between the visible light irradiation, recombination, heterojunction, transfer, and also SRD, which might imply the challenges and strategies for producing high performance visible light active photocatalysts. So there are a few strategies, there are a few challenges that being facing by the photocatalytic for the photocatalytic activity. So the challenges are light absorption, which is it have a limited light absorption. It have a small surface area, and also it have an issue with the charge separation. And all these challenges can be overcome by this strategy, which is band structure modifications, morphological control, and also heterojunction. So in this specific topic, I will just focus on the heterojunction. Since heterojunction able to enhance the interfacial charge transfer, improving the charge separation, inhibiting the charge carrying combination, and also increase the surface area. So there are a few types of heterojunction. So what actually heterojunction? So heterojunction is an interface between two layers or region of dissimilar semiconductor. So there are a few types of heterojunction. We have type 1, called as a straddling type. We have type 2, which is a staggered type, and also type 3 is a broken gap. So between these three types, so type 2 is the one that is the very considered as an effective structure for improving the semiconductor photocatalyst performance. Why? Because this type 2 prevent the charge carrier recombination by creating the spatial separation of electron and holes. While for type 1, you are when you are producing the type 1 heterojunction, there is a possibility of electron and hole recombination. While for type 3, which is the broken gap, there is no transmission or separation of electron and holes between semiconductor A and semiconductor B. Okay, another promising or interesting types of heterojunctions is type 2p and heterojunction, and also direct Z scheme heterojunction. So my research is focusing on these two types of heterojunction, and I will share with you all this heterojunction that we have prepared, which is P and P heterojunction. So the P and P heterojunction that we have prepared is bismuth ferrite, zinc oxide, and BiOCl. And another one is BFO, SNO2, then oxide, and also BiOCl. We have prepared the ternary nanocomposite of P and P heterojunction. So this part of this research has been published in this chemistry selects. So we prepared the ternary nanocomposite via salt gel optocombustion method. So this figure 1.1, shows the synthesis method using the salt gel optocombustion method. We use citric acid as the chelating agent or combustion agent, and then the metal salt. And then next we produce the salt, and then formation of gel, heat at 370 for the combustion process, and then we calcine it to produce the end product. So the synthesized nanocomposite then were subjected to different types of characterization, and including the XRD. So we have characterized the synthesized powder via XRD, and the XRD result confirm that the SNO2 and BiOCl coexist with the BFO in BSB15 sample. So this is the BSB15 sample. And below is the GCPDS for SNO2, zinc oxide, and also BiOCl. So all the three elements consist in the ternary nanocomposite and also coexistence of BFO, zinc oxide, and BiOCl phases in BZB15 sample. So all the sample also exist in the ternary nanocomposite, which confirm the successful formation of ternary nanocomposite of BFO-based photocatalyst. We also conduct the optical analysis using the UV-Vis and also photoluminescence spectroscopy. So from the UV-Vis analysis, this is for the black color, OA is a pure BFO, and then the blue color is for BSB15, and the C color is a BZB15. So what we want to highlight here that all the synthesized photocatalysts exhibited a strong light absorption in the visible light region. So all the synthesized photocatalysts have absorption in the visible light region. And then for the PL, photoluminescence spectroscopy, so the blue one is for pure BFO, bismuth ferrite, and then for the green one is for BSB15 and also BZB15. So 15 is represent the loading of the photocatalyst. Okay, the PL, so the result shows that the PL of BZB15, the red color, exhibited the lowest peak intensity than that of pure BFO and also BZB15. So this indicates the lowest recombinations of the photo-induced charge carrier, which indicate that BZB15 is better than BSB15 and pure BFO for the photocatalytic degradation application. So this means that these types of photocatalyst, which is BSB15, has the lowest electron charge recombinations. And then the result shows the photocatalytic study of the synthesized photocatalyst. We have the result for different loading of zinc oxide, different loading of zinc oxide in the ternary nanocomposite, and also different loading of tin oxide in the nanocomposite, the photolysis data, and also the pure BFO. And then from the photocatalytic study, it is found that the BZB15 sample show excellent photocatalytic efficiency than other sample, where complete degradation was achieved in 60 minutes, followed by BSB15. So the blue color, the triangle blue, is represent BZB15, while BSB15 is from the dark blue color. So this is might due to the high surface area. So we also characterize the ternary nanocomposite via WITA analysis to get the surface area. So the BZB15 has 15.1 square meter per gram. Sorry, the surface area, and compared to BSB15 is 11.5, and pure BFO is very low. Surface area is 1.63. And also is also attributed to the lowest electron hole recombination in BZB15 from the PL results. And also we also conduct the TOC analysis. TOC is were conducted to determine the mineralization of the RB5, which is our target contaminant, RB5 dye. So from the TOC analysis, it is found that there is the TOC conversion is high, very high for the BZB15 after 90 minutes, which is 99.5. So this means that the dye was discolored and mineralized. So both post-process are happened, discolorization and also mineralized, and signify that beyond 90 minutes of irradiation may lead to complete mineralization. So we may able to get complete mineralization if we do the reaction times more than 90 minutes. Then we conduct the HPLC analysis. HP analysis was performed to confirm that CR degradation by BZB15 had occurred. And from the HPLC analysis, so the upper one is the HPLC spectrum before treatment, and the lower one is the HPLC spectrum after treatment. So the CR control sample shows a prominent peak at the retention times at 1.4505 and some very small peak at retention times at 2.415, 3.538, and also 5.876 minutes. And however, after treatment for 90 minutes, the dye control peak disappears. So you can see that the control peak disappear, and also there is a new peak appear at the different retention time, which is 1.344, 2.718, and other small peak, which is 3.178, 7.448, and 9.89 minutes. So the disappearance of the control peaks and also several new peaks in the treated sample suggests the degradation of dye-CR into different intermediate metabolites by the ZBIN15 nanocomposite. Okay, next we also conduct the radical scavenger study. So radical scavenger study is conducted in order to find the possible mechanisms of the photocatalytic activity. So in the experiment, we use benzoquinone, ammonium oxalate, and also isopropyl alcohol as a scavenger to capture active superoxide radical, whole, and also hydroxy radical respectively. So from this graph, you can see that superoxide radical and whole, these two, superoxide radical and whole, were the main active species responsible for the degradations, while hydroxy radicals play a secondary role in the reaction. So from the radical scavenger study, then we can come up with the possible charge transfer mechanism. So for the transfer pathway mechanism of the charge of the photocatalyst follows the P and P heterojunction for the ternary nanocomposite. We found that the mechanism is via P and P heterojunction. So the under visible light radiation, the photoinduced electron on the conduction bands of the BFO and BIOCL. So this is for BIOCL. This is for BFO. The conduction bands are injected to that zinc oxide. So it will be injected into zinc oxide, while the hole in the valence band for these two semiconductor will remain. So the oxygen that traps on the conduction bands of zinc oxide produce the reactive superoxide radical. So in this area, it will produce the superoxide radical. The superoxide radical may directly degrade the dyes, or it may react with the H+ to form OH, followed by rapid decomposition to OH. So the holes in the N-types valence band, so the hole in this area in the N-types valence band of zinc oxide will move to the valence band of the P-type semiconductor. So this hole will move to the BB of the BIOCL and BFO, which result in high separation rates of the photo-induced charge. Moreover, the holes may react with the surface-bound H2O. So the hole here may react with the surface-bound H2O, or to generate the hydroxy radicals, or could directly oxidize the dye pollutants on the valence bands of the hole here, because the hole will be transferred in this part BB of the BIOCL and BB of the BFO. And nevertheless, the affinity of photo-induced hole to attack the contaminant directly is faster than the rate of formation of OH radical. So as a result, holes significantly contribute to the photocatalytic reactions, while OH radicals serve as secondary function. So the rate of recombination of the charge carriers will be reduced, and the visible light performance of the BZP15 composite for CR degradation will significantly improve. So this is the mechanisms of the P and P heterojunction. Okay, next is the direct Z scheme heterojunction. So in our lab, we also have prepared direct Z scheme heterojunction using Cu2O, zinc oxide, and we combine with the semiconducting polymer, which is polyaniline, PANI. So this research has been published in Journal of Environmental Chemical Engineering. So the synthesized ternary nanocomposite were subjected to SRD analysis. This is to confirm that all the material or all the semiconductor are exist in the ternary nanocomposite. So this is the below one is the pure PANI, the XRD pure PANI, and also zinc oxide and also Cu2O. So from the ternary nanocomposite XRD spectra, so you can see that the sharp peaks indicate that the resulting CZEX was well crystallized and the zinc side phase coexists with the cubic C2O phase in the composite. So this is from the CZEC and for your CZP. So Pani peak appear very low and most of the intense peak present are almost all attributed to Cu2O and zinc oxide. And this is because the amount of Pani is low and its diffraction peak are much weaker than the crystallite Cu2O and zinc oxide because of the amorphous nature of Pani. So as we know, Pani is in amorphous state. So that's why we cannot detect the Pani peak in the 6xp nanocomposite. So below is the table shows the surface area from the BAT analysis. So it can be seen that the surface area for the ternary nanocomposite is higher, which is 45.32 compared to pure C2O and compared to the binary nanocomposite, which is CZ 35.66. So the higher surface area usually we contribute to a higher photocatalytic efficiency. So in order to confirm that Pani is exist in the ternary nanocomposite, we conduct the Tga analysis. So the pure form of Pani was reported to degrade at 200 above 200 degrees C. So from the Tga analysis of the ternary nanocomposite, which is CZXP, cuprous oxide, zinc oxide, and also Pani, it can be observed that there is a significant wet loss at region of 200 to 500 degrees C. So you can see a significant wet loss here at around 200. Here, first one is at 200 and the other one is around 300 degrees C, which is indicator of the burn of polymer formed on the surface of the photocatalyst. So this implies that Pani was deposited on the surface of the CZXP composite, while the composite can be said to comprise of about 28% of Pani content. So we confirm that we have successfully produced a ternary nanocomposite. So then we conduct the optical analysis, optical properties. So this is the UV-Vis and IR absorption spectra for Cu2O, CZ and CZP, the figure A, while B is the top plot for Cu2O, CZ and also CZP. So from the UV-Vis analysis, all the synthesized photocatalysts exhibited strong light absorption in the visible light region. You can see from here. And then the band gap corresponding to the phase of Cu2O were found to be around 1.93 electronvolts, while that zinc oxide and Pani were found to be at approximately 3.13 and also 2.2 electronvolts. So from the ternary nanocomposite, we are able to find the band gap for all the material, which is C2O, zinc oxide, and also Pani. And the right side is the PL spectra for the Cu2O, binary composite, CZ, and also ternary nanocomposite. So Cu2O shows a strong emission peak centered at around 450 to 570 nanometer under 315 nanometer excitation. So from this PL analysis, it can be found that CZP has the lowest intensity than CZ and also Cu2O, which signifying the lowest recombination and also might contribute to enhanced photocatalytic activity. So from the photocatalytic study, so we conduct the photocatalytic study using CR, overhead dyes, and also under visible light irradiation. And this data shows that we varied the loading of the aniline since we prepare the CZXP using the in situ polymerization. So the sample containing 0.1 milliliter aniline have the higher photocatalytic activity. So the pink color, this one is represent the CZP that consists 0.1 ml of aniline. So the photocatalytic activity increases with increase in aniline until it reached 0.1 milliliter. When the amount of aniline was increased to 0.13 milliliter, the photocatalytic activity reduced significantly. So this the brown color is aniline at 0.13. So the reduction in photocatalytic activity by CZP 0.13 can attributed to the excessive amount of Pani which may form a closed shell on the surface of CZ, thereby heat inhibiting the catalyst contact with the pollutants and subsequently reduce the light activity of the catalyst. So from this study, we found out that 0.1 is the optimum amount of the aniline to be used in the ternary nanocomposite. We also conduct the radical scavenger study. So the same objective as the earlier part, which is for the PNP heterojunction. For the same heterojunction, we also want to find the possible mechanism. So the radical scavenger study were conducted. So in the experiment, we use the amino oxalate, benzoquinone, and also isopropyl alcohol. Were used as a scavenger to capture the active host, superoxide radical, and also hydroxyl radical. And again, from the study, we found that host and superoxide radicals were the main active species responsible for the degradations, while for the hydroxyl radicals play a secondary role in the reaction. So from the radical scavenger study, then we come out with the possible charge transfer mechanism. For these types of nanocomposite, the possible charge transfer mechanism follows the dual channels of the charge transfer. With the illumination of visible light, CO2O, zinc oxide, and pani will absorb the photon of light to produce electron and holes. So the electron produced on zinc oxide, this one is zinc oxide, the middle one, have less reduction potential than the electron on the Cu2O, the right side, and pani in the left side. As such, it will rapidly quench the hole with less oxidation potential on HOMO of pani and valence band of Cu2O. So the electron here from the it will fits. I would like to remind you all that you can put your question if you might forgot about your question, because we have 4 speakers after all. So if you are afraid for that, you can put your question in the chat box. Or absolutely, you can ask directly to the speakers after the last session.
Okay, first of all, I would like to thank the organizer for inviting me to be one of the speakers today. So this event is very wonderful experience for me. So I would like to congratulate the organizer for organizing this kind of event. So I believe that this event can be the platform to initiate our collaboration in future. So today I would like to share with you the topics on the photocatalyst with energy storage properties for the efficient organic pollutant degradation. All right, so as for the introduction, the ever-growing global concern about the wastewater treatment has played important roles in controlling a massive amount of wastewater. So most of the wastewater are contain a lot of complicated compound where we need to degrade this kind of compounds so that at the end, the effluent must contain a very low hazardous product, such as it's come from the pharmaceutical, personal care product, EDC, pesticide, and also from the textile industry. So recently, the increasing of the level water pollution, so we know that it's contribute a lot in our environmental issue, and it's trigger the topic. I would like to focus on the use of the tungsten traps, where this photocatalyst is contribute to extraordinary characteristics of the photocatalysis degradation, photostability, high crystallinity, high yield, and recyclability, and also can be one of the material as energy storage substance. Okay, one of the method that most of the research looking for catalysis reaction can be continued. Okay, when we talk about mechanism, in this RTCP system, we will involve into 2 main mechanisms, where it's involved electron storage mechanism and also involve the whole storage mechanism, so that the catalysis will continue under the dark condition. Okay, the example of the photocatalyst that have or that imply the electron storage mechanism is titanium dioxide combined with the tungsten trioxide. Okay, this photocatalyst store the electron through a formation of the intermediate product, where the TiO2 function as a light harvesting and WO3 as a electron storage material. Okay, under the light irradiation, whether UV or visible light, the electron hole pair are generated in TiO2. Okay, photocatalysis of zinc oxide combined with silver nanoparticles. So the result demonstrated that the electron delay is happened due to the electron storage that keep the electron for a longer time for the silver nanoparticles. Okay, the third one is carbon nitride. It's reported that the electron was stored through the formation of long-lived radical. Okay, so for the formation of intermediate reversible product, capacitive nature, and also the formation of long-lived radicals. So those three electron storage is fall under the electron storage mechanism. Okay, however, mechanism of electron storage in some of the material, such as bismuth, is still very rare reported. Thus, the systematic study are encouraged to further understanding the mechanism. So actually, there is a lot of semiconductor. Now, they're not reported yet on their capability of the electron storage mechanism. So this can be one of the topic that you can explore in future in the photocatalysis field. Okay, now we look into second main mechanism. They involve a whole storage mechanism. For example, when you have a combination of titanium dioxide with nickel hydroxide. Okay, similar to electron, the whole also can be stored. So how it's stored? Under a light excitation, the photo-generated whole will be transported into a bag of nickel hydroxide. Whole storage mechanism, it also can be found when you have a combination of titanium dioxide with NiO, nickel oxide, and also TiO2 and CiO2. Okay, the whole storage efficiency, when we compare with the electron storage mechanism, it is reported that the electron storage mechanism is more efficient. So we can say that TiO2 tungsten trioxide is more efficient as compared to TiO2 nickel hydroxide in the dark condition for the photocatalysis. It is due to the loss of whole by adsorbed water oxidation or re-reduction of nickel oxide by the photo-generated electron. However, we can also modify or enhance this kind of lacking on the TiO2
what we are looking for example, for degradation or renewable energy application, energy storage, and so on. All right. The third one is their electron hole separation efficiency. Okay, for the third one, if we are unable to get a more stable and enhance the half-life of the photo generated electron, meaning that from the valence band to the conduction band, we need to separate them so that they're not recombined. So if they recombine, so this no point, because the reaction cannot be proceed and so on. So the last but not least, I think for low cost applications, low cost synthesis, processing, low cost materials, and I think they are looking for, when we talk about industry, it's all about money, right? So industry always want to have low cost, but they want to have more profit, right? So this is the thing, how industrial parties think about this kind of material development or for application. I think that's all from me. Thank you so much.
Okay, thank you for your comment, Dr. Azuwa. So this is challenging, but promising also. It's kind of confusing. So if how about in Japan? Maybe Professor Sadaki Samitsu has any perspective.
Thank you for a comment. So first of all, thank you for the question of the photocatalytic application. So my additional viewpoint is how to make a system from the viewpoint of chemical engineering. So also the material is efficient, but from the chemical engineering, making a system is another viewpoint. For that viewpoint, the construction of the material structure as well as a device is is another important aspect. I think, yes.
Okay, thank you. Maybe Dr. Norharyati, you want to give an opinion?
Yeah. Okay, I would like to add, in terms of the other than electron recombination, they also have one more challenging in terms of the intermediate products. So let's say you would like to degrade one of the hazard product. So during the photocatalysis, most of the time you also degrade other byproduct which is more hazard as compared to the root of the compound. So that one also one of the challenging in order to get the high purity or a zero EDC content inside the wastewater. So we need a longer times, and also the process as mentioned by the Dr. Sadaki, we have a high technology of the system in order to tackle these types of the effluent. And for example, for the pomade itself, whether the EDC content is very low, but the volume of the wastewater is very big. So in terms of the system, so it's still lacking on that kind of technology. So where we have a high performance. Okay, I think in terms of the intermediate, that is one of the difficulties for the commercialization. All right, thank you.
Okay, thank you. Actually, I have given information that Dr. Farhana and Dr. Juhana couldn't attend this discussion session. So because there are any other agenda. So if everyone wants to ask question to two speakers, could drop the question and I will send them to their email. So we continue the discussion, please. Does everyone have a question, more question? Maybe, can I ask a question? Just wait for another attendees to ask. Actually, what is the challenge to develop a commercialized one. I think a collaboration industry is another obstacle, but what is important thing that you have to achieve and industrial want to use that materials? Please, everyone want to.
Yeah, maybe you can start with me.
Sure, sure.
So basically the same, actually the same thing, like have been mentioned by Professor Sadaki, Samitsu, and also Dr. Norharyati. That is correlated, thing that we need to consider before we pushing this technology towards the commercialization and so on, right? So like we have, like in terms of material development, okay, so if we do have a very appreciated, if we find that this certain material is very performed, and then like have been mentioned by Dr. Hayati just now, because of the intermediate product. So if we can design the photocatalytic material that have a very specific selectivity, yeah, so yeah, so that one is can be overcome in order to have what we call it, a clean water and so on, right? Apart from that, the thing as been mentioned by Professor Sadaki in terms of maybe in terms of reactor design, okay, so this is very correlation to each other. So, but from my point of view, okay, from my point of view, if we able to find a very good, efficient for the catalyst materials, definitely we go with the different kind of reactor or something like or others. Yeah, as long as the material itself can be performed, regardless type of pilot, reactor and so on. I think this one can be commercialized in the future, inshallah.
Sure. Materials with high selectivity. Okay, I find it out. Okay, we have a question from the chat box. So this is from Shafika, UTM Malaysia. Thank you for conducting such a very nice event. The question is, what the opinion of using photocatalytic process in degrading microplastic? Okay, this is interesting. So everyone want to answer?
Oh, maybe I can give
Sure.
a feedback on that. All right. So when we talk about microplastic, it's all about macromolecule. Okay. So basically, we can degrade this kind of thing from our environment. However, so far at the moment, due to the a bulk molecule, so it would take a longer time. So basically to degrade them, even though we have a biodegradable plastic, for example, but still they need to have a certain time to degrade that kind of very big molecule. All right. So like I say, if we able to find a very good catalyst that can degrade that thing in a shorter time, I think we can solve the problem. Thank you.
Okay, I think because we all know that plastic is not easily degrade, something like that. Maybe we can produce some catalyst to degrade microplastic. It must be useful. Maybe Dr. Norharyati or Professor Sadaki has an experience about degradation of microplastic. Prof. Sadaki, I think.
Thank you. Thank you for
your
a very
field.
interesting question. So my viewpoint of the this issue is concentration of the microplastic is very low, and as Dr. Muhammad mentioned, degradation efficiency of the such large colloids is very slow compared with the molecular system. So I think that one of the important points is for microplastic is a separation or concentration of the microplastic from the wastewater using the membrane technology. Then you can apply the efficient degradation for such a high concentration wastewater, microplastics. That's my point. Yes, thank you.
Okay, thank you, Professor Sadaki. I think it's difficult because we need to separate by using membrane technology. Okay, maybe Dr. Norharyati wants to join to give some opinion.
Okay, in terms of this kind of materials, I don't have any experience on that. So probably the concentration of the amount of the pollutant as well is one of the biggest issue as mentioned by Prof. Sadaki. So at the moment, I'm not focusing on that, but if they are very low concentration, it's very difficult to know that whether we can, or what we have degrade and how many degradation has been happened.
Okay, thank you. Okay, does everyone have another question, please? Okay, hopefully the answer can answer your question. Maybe Dr. Purwanto wants to ask a question.
Thank you, Mbak Lala. For my question is how to strategies for the development of this research and get grants winning in the national or international. I think that.
Okay, thank you. Who wants to answer first? Professor Sadaki, maybe? Your research worth million Japan, yen Japan.
So maybe there are several directions to get a research budget, but your question is how to get a research budget, is right?
Oh,
yeah, the strategy.
And
strategy, yes.
Opportunities for collaboration research with other institutions, maybe.
Okay.
Budget.
So for the getting research budget by the international corporation is important is to understand the strengths of each researchers and find the best collaborative team for conducting the research. Because my profession is actually the material science, and maybe someone is a professional for chemical engineering, and someone is very famous in the chemistry or something. So such a combination of the team is very important for getting a good high price budget in the international as well. I think.
Maybe any opportunities for my institution for collaboration with the consortium research with your institution, Prof.
Thank you. Yeah.
Okay, thank you, Prof. Sadaki. Maybe Dr. Muhammad Azuwa could add something beside Professor Sadaki mentioned.
Thank you so much. Okay, so basically, I am very quite young researcher, basically. So actually, granting a research grant is quite tough. Okay, because nowadays we have what we call it competition among us actually. All right, so that's why what I believe is that we need to develop our profile. Okay, so because I do believe certain grant giver looking for a well-established researcher Okay, so that researcher have promising experience to conduct certain experience and so on. So that's why I'm saying that we need to build our profile. Okay, so apart from that, we need to be aggressive as possible, looking for research grant. Okay, from industry, or from our government, or our from the international. So we need to be alert as alert as possible. So sometimes for grant opening, we didn't aware. Oh, certain grant is have been open now, if calling for the proposal and so on. So we need to have capability to be alert as possible, to check from the website and so on. So we must be active as possible. Okay. So apart from that, when we talk about grant from the industry, so maybe what we can do is that we visit the industry first. We go to the industry, ask for their problem. What are the problems that can we help your industry or your company at certain specific aspect. So I think if we have that kind of strategy, of course we need to have a good team as well. So I believe that when we talk about group research group, we need to have a dynamic research group. So you need to do have a lot of collaboration, maybe with in the university, maybe university in our country, and also maybe collaboration with top researcher from all over the world. Okay, so maybe in the future I would like to collaborate with Professor Sadaki. Maybe I will email you or later because I have some interesting topic because of your presentation just now. So maybe I can keep in touch with you, Prof. So we can discuss for a future collaboration. So this is the thing that we can strategize our winning a research grant and so on. Okay, thank you so much.
Thank you, Dr. Azuwa. I think everyone here wants to collaborate with you, Professor Sadaki. So it's a pleasure to have you here. Okay.
Thank you very much. Yes.
Okay, maybe Dr. Norharyati have another.
All right. In my point of view, probably we can look into, for let's say, for example, we were looking for a Japanese grant. So we need to know what is the environmental issue that they are focusing now. And for example, for the France, so we need to look at what is the main issue that they are now, the research are currently published on that region or country. So this is one of the things that we can propose our materials. So for the photocatalyst, I have tried for the Japanese Kurita and also the Nippon. They are using an inorganic material base. So we also need to look into their aims, their scope, and the material so that it suits the criteria of the grant. So basically, I like the Japanese grant because the proposal is very simple and straightforward. So this is how you need to come up with a very catchy proposal with 1 or 2 pages only. So if you can manage to highlight all the capability of your product or technology, I think we can try. So we can get that grant from the international grant. So that one is for the international grant. So also we need to have a collaboration. So this platform is one of the initiative for us to be continue to collaborate in future, probably because all of us here are doing in the photocatalyst fields, right? So we can look into other types of the grants. Okay, for as mentioned by Dr. Azuwa, we also need to alert because the cycle of the grant opening is different from each region. So mostly from our side, we need to look into. And for the UTM itself, RMC research management, every month they are call for the grant opening, they remind us and keep giving a talk on how we can come up with the very strong proposal So I think by attending the tips and tricks from the previous recipient, so that one also one of the very valuable strategy in order for the next hour for in granting the grant founder outside of the Malaysia. Okay, that's all from me.
Okay, thank you for all the answer. I point 3 from your answer. First is knowing the reason issue, especially if you have a collaboration with industries, and then collaboration with higher impact researchers, maybe like Professor Sadaki Samitsu. Thank you for coming here. And the last is stay alert with any opening of grants, because I think we have numerous grants, but we don't know when and how to achieve that. So please stay alert. Okay, because we have a limited time to discuss, so I would like to appreciate all of the speakers today with certificate of appreciation. This is for Associate Professor Dr. Juhana Jaafar. Thank you for participate. And then Professor Dr. Sadaki Samitsu. Thank you so much. Dr. Muhammad Azuwa Mohamed. Thank you so much also. Dr. Farhana Aziz. And the last, Dr. Norharyati Salleh. I will give you the certificate via email. Thank you so much. So this is an unfortunate moment. We are at the end of the speech session. Hope you get the inspiration from today's event. I deeply apologize if there are inconvenient words. I am Gusti Mindia Nurtajala. See you at the next event. Back to MC. Thank you so much.
Thank you for the amazing speeches from the speaker and lively discussion for the participant. Thank you also to our moderator, Gusti Umindia Nur Tajala STMT, for leading the speech session perfectly. I want to remind all of the audience to fill out the attendance then our committee provide in the chat box. Thank you for all the participants who attend this and the world-class professor meeting series. Finally, we are in the end of the webinar. Hopefully, this event give your inspiration and new insight about the recent development on efficient and effective membrane research for enhancing publication and grant winning. We apologize if there are any mistakes from the committee. We need your feedback to improve your quality or event. Thank you very much for your kind attention. Have a great day. See you on the next webinar. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof.
Thank you so
Thank you very much.
Can we have a group photo first before we end the call?
Oh, sure, no problem. So everyone,
yeah, please
okay.
switch on your camera, please. Yeah, thank you so much.
Please switch on the camera, please, everyone. We have another photo session before we end it. Okay, so everyone want to join? Okay, let me capture the first page. 1, 2, 3, give smile. Okay, wait a moment. Okay, and then this is the second page. Okay, thank you so much.